So as I've done before, I'm going to work through exam 4. Most of you scored well on it, quite a bit better than previous exams, but maybe there are a few things there for you to learn. And maybe I'm not going to work them all the way out. I'll show you kind of what you should have done, the key to solving these problems. So the first problem, we have 4 antiderivatives. All of these require the work we did with substitution. And all of the problems, I think, are slightly different from one exam to the other. This is, I think, the 3rd version of the exam. So problem number 1A, the key here is, we have secant times tangent, and we should recognize that as being the derivative of secant. Some of you had secant squared here, you would recognize as the derivative of tangent. And the first exam, I think, had a different version. The problem here is the 2 here. Can you show me how to deal with the 2? So that's where substitution comes in, and you want to let u be 2x and then immediately calculate the dx, the du. And so because of this 2 right here, our answer is going to be 1/2 secant 2u. Secant u, which is 2x. And then you could add your plus c. Over here, the key is to substitute for the bottom. Notice we can get the derivative of the bottom on the top with just juggling a few constants around. So we get a 14x we really don't need. And we got a 9 here we can't really use. So we're going to pop that 9 through, and then we're going to multiply by 14 over 14 so we can cancel that 14 out, which is going to get me 9/14. As soon as I can get the function on the bottom, I can force its derivative on the top, then that's just going to be a log. And 7x squared plus 25 can't be negative, so no absolute value signs required. On part C, we want to substitute for 4x. And du then is 4 dx, and then you get 1/4 the integral of the square root of u du, and I'll let you finish it. And similarly over here, we let u be minus 3x, and then du is minus 3 dx, and that gets us minus 1/3 the integral of e to the u du, which is a nice easy problem. And we can probably finish. So it's not all the way, but it kind of shows you what to do. On question number 2, we get a chance to use the fundamental theorem, and actually no substitutions required here. Well, maybe on part A, depending on how you look at it. We have this 3 on top, and then we don't really need that, so we're going to bump it through. And then the integral from 1 to 4, I have 1 over x plus 6 dx. And if you notice, the derivative of the bottom is 1. So it's all perfectly set up. Unlike this problem here, part B, we can force the derivative of the bottom on the top by juggling the 9 and the 14. But on this problem, the derivative of the bottom is 1. And so therefore, we can just go straight to the antiderivative, which is going to be the log x plus 6. And we'll go from 1 to 4. And then just do the arithmetic. You could do this by substitution. You could let u equal x plus 6. And then, of course, du would be dx. And then the integral you would get would be 1 over u du, which is obviously a log. But because the derivative of x plus 6 is 1, you don't really need to do the substitution. I have nothing to say on part B. Nice and simple polynomials. This question is just, do you know how the fundamental theorem allows us to find the value of these integrals? And most of you did, of course. All right, for page 2.